Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This is another video on areas and distances in Calc 1 differential calculus. This is probably a good set of videos also to review when you enter into Calc 2 because you really want to know what you're dealing with in Calc 2. I'm not going to say the word, I'm just going to say what you're dealing with in Calc 2. So let's go ahead and actually use all the theory we've developed up to this point to compute areas underneath curves. So this is more of the applied style of problem. When you're starting to do homework, this is what you're looking at. So computing areas underneath curves using Riemann sums. And remember, just off to the right here, I'll write it down. The Riemann sum is this summation right here. The sum I equals 1 to n of f of x sub I star times delta x. And again, I use a x sub I star because I just don't know if you're using right endpoints or left endpoints or midpoints or whatever. And again, this will be the video where I introduce midpoint method, by the way. All right, so consider the area under the curve y equals x cubed plus 2 from x equals 0 to x equals 1. This one I can actually graph by hand, and I'll do a terrible job of it. And it wasn't too terrible, actually. So this is the graph of y is equal to x cubed plus 2. It doesn't look like a cubic because I've scaled it differently than what you're used to. I scaled it so that I can just fit it on the screen. When x is 0, y is 2. When x is 1, y is 3. So that kind of works out, right? So this is a height of 3, roughly right about there. All right. So let's see what we're being asked to do. Estimate the area underneath this curve using r sub 5. That means we're going to be using right edge points and we're going to do 5 slices. So again, we have the formula up there, but I didn't write down all the extra little bits. The extra little bits are as follows. The width of each slice, I was going to say the average width, but it's just the width of each slice, is b minus a over n, where n is the number of slices that you have, and x sub I is going to be a plus I times delta x. That will all be important. So r sub 5 as a formula is just going to be that Riemann sum. I equals 1, but we'll end at 5 because that's what n is. And we're going to look at f of x sub I times delta x. The reason why it's f of x sub I is because we're using right edge points. Let me showcase that here. Normally you would not be able to actually draw out all the slices that you need, but since this is the beginning of us learning about this, it's good to kind of see each of these slices. So you could see that I have 5 slices, right? Here's the first, here's the second, third, fourth, and the 5th slice. Each of those has a width of 1 minus 0 over 5, or in other words, 1/5. That's the width of each of those slices. And if I want to use right edge points, then, for example, in the third interval, because it's more obvious there, using the right edge point, we have something like this. This will be the rectangle we're going to use to approximate the area of that third subinterval. Now, that third subinterval starts at x sub 2 and ends at x sub 3, mainly because our first interval starts at x sub 0 and ends at x sub 1. Right? And then there's x sub 2, x sub 3, x sub 4, and then the last one is x sub 5, which is 5 because of our number of slices. But the main thing to note here is when you're finding the area of the, for example, third slice, you're going to evaluate f at x sub 3. So that's why when I want the area of the ith slice, it is x sub I. That is the formula for the right endpoints. It's just a simple formula, f of x sub I times delta x, and then you're adding up all those edges, right, or all those areas. In this case, it's pretty easy to compute because, again, our average step size is 1/5, or basically our step size is 1/5. And so we start at 0. The next edge is going to be 1/5, and then 2/5, and so on and so forth. So let's go ahead and just rewrite this Riemann sum. We'll expand it out, and we'll say, okay, well then that's f at x sub 1 times delta x plus ... until we get to f of x sub 5 times delta x. Notice all of those terms will have a delta x in common, so you could actually factor that out back. It's faster that way, it's cleaner that way. So we have f of x sub 1 plus f of x sub 2 all the way to f of x sub 5. Now we just need to figure out what those x sub 1s, x sub 2s, all the way through x sub 5. And in this specific case, we could see them. It's going to be f of x sub 1 is 1/5, then 2/5, then 3/5, then 4/5, then 5/5. However, you probably want to remember this formula. X sub I is a plus I delta x. In this case, a is 0, and delta x is 1/5. So if I want to know what x sub 1 is, it's just 1/5. X sub 2 is 2/5, and so on and so forth. It's just kind of easier to compute that way when you get to large computations. So this will be f of 1/5 plus f of 2/5. That sets the pattern, and we go all the way down until we get to f of 5/5, which is 1, times delta x, which is 1/5. And then we just need a calculator. Honestly, that's the only thing you're going to use here is a calculator for this, because there's no way you want to do this by hand. So in this case, we'll go ahead and write it out just so that if you have a hard time understanding the mathematics behind the scenes, f of 1/5 is 1/5 cubed plus 2, because that's the function, x cubed plus 2. And then the next one will be 2/5 cubed plus 2, and so on and so forth down the line until you get to 1 cubed plus 2 times 1/5. So let's go ahead, that's times not minus, and compute this. And this time I am actually going to go ahead and show you how I would use Desmos for something like this. So right now I'm in Desmos' scientific calculator. I would probably just say f of x is equal to x cubed plus 2, just to set the function. And then remember, it was the quantity f of 1/5, oops, don't need that there, plus f of 2/5 plus f of 3/5 plus f of 4/5, and then finally plus f of 1. And that whole thing was multiplied, don't forget this is very important, this whole thing was multiplied by 1/5. And there we have the area is approximately 2.36. And before I head back to my other screen, I just want to give you a heads up, there's another way to compute this. I'm just not doing that right now, but I'll show you in a little bit a better way to compute this. Now back at my laptop screen here, I just want to showcase that I said this is strictly equal to 2.36, and it is true. That's what r sub 5 is actually equal to. The area underneath that curve, the signed area, is approximately that. That's what the area is approximately. It's not exactly that, but r sub 5 is definitely equal to 2.36. So there you go. That's using the Riemann sums to estimate the area underneath a curve. Now this question is usually reserved until a future section, but I actually like this for this problem. I want to get your brain primed for what you're going to see eventually. So find a general formula for r sub n. Remember, r is the right endpoint method, and in this case, they're not telling us how many slices that we're using. So we have to kind of keep everything symbolic. Well, if they tell us that we have that interval from, remember, our function is x cubed plus 2, and it was on the interval 0 to 1, and they're telling us we're slicing it into n sub-intervals. Well, that means that our average width, or width, is 1 minus 0 over n, or 1 over n. Also, this tells us that x sub I is going to be a, which is 0. Well, actually, maybe I would write a here. A plus I times delta x, but a is 0, plus I, and delta x we just computed is 1 over n. So x sub I is just I over n. Now, I happen to know the formula when you use the right endpoints. The Riemann sum formula is this: summation I equals 1 to n, because we're doing n subintervals, f at x sub I delta x. Now, we're going to insert this information that we have here. We know that x sub I is I over n. And let's go ahead and insert that in there. So this is a summation I equals 1 to n of f at I over n. Not bad, actually. Right now, seems pretty safe. And then delta x is 1 over n. Let me insert that in there as well. Times 1 over n. Something I need to draw your attention to. So summations are sort of like limits in that they only really mess around with stuff that involves their indices. So like a limit as x goes to infinity. Well, if you had a limit as x goes to infinity of something that doesn't involve x, well, then the limit doesn't apply to it. So let me go ahead. I'm trying to erase that highlighter, but it just wasn't working. So let's go ahead, and I'm just going to say that again. Limit as x goes to infinity of h, for example. Since h does not involve x, that's just h times the limit as x goes to infinity of 1, which is just h times 1. So because that limit did not involve actually x values, well, it does nothing. There was no point in writing the word limit or the operation limit. Same thing here. If you have a factor that doesn't rely upon this index I, there, write it that way, then you can move that factor outside. And that factor in this case is 1 over n. So I can just say, you know what, that 1 over n that's multiplying each term, that does not really, I does not actually affect that. So I still can factor that out, and I have the summation I equals 1 to n of f of I over n. But we know what the function f is. It's x cubed plus 2. So I'm going to go ahead and say that this is equal to 1 over n times the summation I equals 1 to n of our x cubed plus 2. And x in this case is I over n. So I'm going to do it this way. I over n cubed and then plus 2 is what we had on there. And one last little move before I start going crazy. And the last little move is this. It's 1 over n, and we have a summation I equals 1 to n of I cubed over n cubed. Well, that's not too bad. Plus 2. And here is where recalling your pre-calculus summation stuff is important. And I tried to tell my students from the beginning of the semester, the stuff you learn in pre-calculus will be used in calculus, and you'll be held to those prerequisites because you didn't just learn them just to keep your mind busy. You learn them because you're going to use them. And my students already go through mathematical induction, which you learn in pre-calculus. And now they're going to be using, right now, the summation formulas. So let's talk about the summation formulas and a couple summation properties. So recall, the summation I equals 1 to n of a constant c. Well, if you're adding a constant to itself n times, then that's cn. So the summation of a constant, if you're adding it to itself n times, is just c times n. That's it. That's going to be very helpful when I tell you that we're summing up 2. The other thing I want to mention, if it's a finite sum, the summation I equals 1 to n of some number relying upon plus a different number relying upon I, well, that's going to be the summation of the first number relying upon I plus the summation of the second number, again, relying upon I. In other words, you can split summations. As long as they're finite, you will, in Calc 2, do summations that are not finite, and splitting those can be a little bit wicked at times, so you might not be able to split them. But that's going to be useful here as well, because, well, I have a summation of I cubed over n cubed plus 2. I'm going to split that sum. In fact, let me do that right now since we're writing down those identities. This is 1 over n times the summation I equals 1 to n of I cubed over n cubed plus the summation I equals 1 to n of 2. Furthermore, I'm going to use that first property that we wrote up there. Where is it? I'm summing up from I equals 1 to n the number 2. So I'm going to go ahead and say that's 2 times n. So I'll just replace that second summation. So let me just quickly write this in here. I'm not going to talk you through it. I'm just going to do it. I cubed over n cubed plus 2n. Okay. There we go. Actually, I'm going to do one other thing here. Since that first summation, its denominator doesn't rely upon n, I'm going to factor out that denominator. I'm sorry, since that denominator doesn't rely upon I, I'm going to factor out that denominator. Sorry about that. So it doesn't, it doesn't rely upon the index of the summation, so I can factor it out. The I cubed still has to sit there, because that I cubed does rely upon the index of the sum. Finally, or second to finally, actually, because I need to remind you of another one. There's a Gauss summation here. Let me go to blue here. Gauss's sum looks like this. I equals 1 to n of I. So in other words, 1 plus 2 plus 3 plus 4 all the way up to n. That is going to be n times n plus 1 over 2. That should have been proved by you or for you in pre-calculus. You can prove this via mathematical induction. It's a beautiful proof. You're welcome to do it. But the one that I want to get to is I cubed. This is another one you should have learned and used in pre-calculus. The summation of I cubed is going to be n squared times n plus 1 squared over 4. In other words, it's the square of that. So, and by the way, there is another summation formula for I squared, but we don't need it here. So I'm going to ignore that. And I'm just going to go ahead and use the summation of I cubed. All right. And if you're looking at these and freaking out and saying, oh my gosh, do I have to memorize all that? You should have had that memorized already. So yes, you are going to have to remember them. You will have to remember at least this group. This square, I tend to not have my students memorize just because it's a little bit off-putting to try to memorize that one, but at least these you should memorize. All right, going down to the formula here where we're at, I'm going to go ahead. Remember, it's often easy to forget what you're doing. We are just trying to figure out a formula for R sub n, the nth summation, or the sum of the n rectangles, using right edge points. For this specific function, what we arrive at here is not going to be for every function, just for this specific function. So we started with our Riemann sum, inserted the values that we've calculated for delta x and x sub I, and then evaluated f at that x sub I, which is I over n. And now we've just been using properties to get down to this point right here. And this is going to equal 1 over, I'll just keep this 1 over n on the outside for now. We have a 1 over n cubed. And then we now have just rediscovered the property that the sum from 1 to n of I cubed is going to be n squared times n plus 1 squared over 4. Now notice you no longer have a summation. This is just algebra now. And now I will distribute this 1 over n into those parentheses. So you get 1 over n to the 4th times n squared times n plus 1 squared over 4 plus 1 over n times 2n is 2. And if you really want to write this nicely, you could say that's 1/4 times n squared times n plus 1 squared over n to the 4th plus 2. All right, so that is a closed formula. That's what we'd call that, a closed formula for r sub n. Now that we know that, let's see what part C of this is asking. Use a limit to find the exact area underneath this curve. Well, remember, in the previous video, I had mentioned that the area is actually going to be the limit as n goes to infinity of your Riemann sum. In this case, our Riemann sum is the right edge points, but it's still the same idea. So we'll go ahead and insert what we just computed for r sub n, which was 1/4 n squared times n plus 1 squared over n to the 4th plus 2. I'll just group all that stuff up. Now, as n goes to infinity, you could divide both numerator and denominator of this very first fraction by n to the 4th. Doing so, you'll get the following. I'll just do it here. This is equal to the limit as n goes to infinity. Again, I'm just dividing the numerator by n to the 4th and the denominator by n to the 4th. Well, if you divide the denominator by n to the 4th, you get this, 1. You divide the numerator by n to the 4th, well, I'm going to split that n to the 4th amongst these two. So I'm going to divide this one by n squared and then divide that one by n squared. So I'll get 1 times n plus 1 squared over n squared and then plus 2. Just showcasing this, I'm taking my time with this really. And that's equal to the limit as n goes to infinity of 1/4 times, let's see, that's something squared. Oh, it's n plus 1 over n, or in other words, 1 plus 1 over n being squared plus 2. And we happen to know as n goes to infinity, 1 over n tends to 0. And so therefore this becomes 1/4 times 1 plus 2, and that will be 9/4. That is the true area underneath the curve f of x is equal to x cubed plus 2. Now that often is a beefy example. A lot of students struggle with it, but you're going to be doing this stuff. So it's a good idea to rewind this, rewatch that, take a look through. The one thing I want to reassure you of is you cannot do this for anything other than polynomials, and their power has to be, or their degree has to be 3 or less. So that's kind of the saving grace. For everything else, we'll have special methods. All right, our next example is just to find the area underneath this curve, y equals negative 3x plus 3 from 0 to 1, using left endpoints, and I should say left endpoints with 4 subintervals. With n equals 4, there we go. So with n equals 4. So we're basically looking at L sub 4. I have to sneak in an L sub 4 somewhere. That's just how it is. So let's go ahead and graph this. And here is the curve, and we're just finding the area underneath the curve from 0 to 4. Now let me give you a heads up. You probably already see it. You can easily find this area. So this is not about actually making it harder than it should be. It's about just getting used to using calculus here. So we're gonna just slice this into 4 pieces, and I'm gonna do this by hand rather than what I've been doing, which is measuring it. So slicing it into 4 pieces, we get something like that. So 1, 2, 3, 4. And we're gonna use the left edges to give us the heights, the caps here, right? So there's the left edges, there's the left edge, there's the left edge. Obviously, this is an overestimate of the area. You could totally see that, right? Remember, the formula, the Riemann sum for the left edges is going to be this, the summation I equals 1 to 4 of f of x sub I minus 1 times delta x. It's I minus 1 because in the first slice here, you're using x sub 0. Let me get down here and just point an arrow. That's x sub 0. This is x1, this is x2, this is x3, and this is x sub 4. Notice, even in the second slice, for example, in this slice right here, you're using the left edge point, so you're actually evaluating the function at x sub 1 for the second slice. So when you find the heights, you're using x sub I minus 1 because you're using the left edge of each slice. It's a good way to think about that. Delta x here is going to, oops, should be a delta x, not just a delta. Delta x is going to be the distance of that interval divided by the 4 because it's the number of slices. And now you can just compute this very, very quickly. So this will be the summation, and I'm going to factor the 1/4 out of all of these, and you get f of 0 plus f of a quarter plus f of a half, and so on and so forth. Now, I'm not really concerned with the value here, just to make sure that you could set this up. I'm sure you can grab a calculator and compute all these values. That's not my concern. My concern is that you can set this up. Then you go to your function and evaluate this. I'm not going to do that here because that's not the point of this. What I really want to do is introduce a new method. So we have the left endpoint rule. And the left endpoint rule, remember, you're given some sub-interval. Your function is maybe doing that over the sub-interval from x sub I minus 1 to x sub I. Not from a to b, but this is a sub-interval of the interval from a to b. Okay. And if you use the left edge right here, then the height of the function at the edge you're going to use is x sub I minus 1, f of x sub I minus 1. If you use the right endpoint method, well then, you'll evaluate your function at f of x sub I. That's the right endpoint method. The midpoint method is going, I looked up at my screen, I could totally tell this is slanted, sorry about that. Anyway, the midpoint method is where you're going to take the average of those two edges, the x value average, and that will be your midpoint. So let me use blue for that. That'll be the halfway point here, in the halfway point of the x value. So that'd be x sub I minus 1 plus x sub I over 2, the average of those two values. And the midpoint method just puts a cap on this at the midpoint rather than at the left or the right edge. Let's go ahead and take a look at this using that Desmos coding that I had earlier. So here is just a weird curve. I just typed this in just to have something different. And we're going to take a look at if you did, let's say, 3 slices via left end method or 3 slices via the right endpoint method. Let me zoom out a little bit. And now we have this new method where you're doing midpoints. Again, there's the right, here's the left, and then you have this midpoint. The midpoint, this blue vertical line is the midpoint of this interval. We have 3 subintervals. It's the midpoint, and you can see I put a cap on that, a top on that at the midpoint. That's the midpoint method. Turns out the midpoint method is much better than the other two because it averages out errors. And so it ends up being incredibly good. But it also is a little bit tough because you have to do extra computing when you're using it. You have to find averages. So you can't just say, oh, let me grab all the left end points and plug them in. You have to average points and plug them in. And that's kind of a pain. Nonetheless, we are going to use it because it's an exceptionally good method to use. So again, our function was negative 3x plus 3 on the interval from 0 to 1. Let's go ahead and use the midpoint method with 4 slices. So in this case, let's pretend that we didn't want to graph this. We just want to mechanically do this. So delta x is equal to 1 minus 0 over the 4 slices, so 1/4. And x sub I in general is going to be a, which is 0, plus I times delta x, which is 1/4, or in other words, I over 4. All right, that being done, hopefully, I over 4, there we go. Now I can go ahead and list out my x values. And that's really what you're going to be doing for the midpoint method. You're going to have to list out your x values so that you can average them and then use those averages to compute the midpoint or the midpoint formula. So I build a little table and I say, okay, well, I have 0, 1, 2, 3, and 4. Remember, when you cut up your interval into n subintervals, in this case 4 subintervals, you'll actually have 5 points because your edges give you an extra point. So x sub 0 is the beginning point, which was 0. X sub 1 would be 1/4. I'm just reading off of this right here. X sub 2 is 2/4, so half. X sub 3 is 3/4, and x sub 4 is 4/4 or 1. See how quick that was? Not bad. And now what we're going to do is compute the averages. And this is just done what's halfway between 0 and 4, basically, or you average 0 and 1/4. So that'll be 1/8. That's halfway between 0 and 1/4. Hard to see there, sorry about that. And then average 1/4 and 1/2, and you'll get 3/4 over 2 or 3/8. And one thing you should notice, so you don't spend your life computing this stuff, is that all you're doing is really adding 1/4, your step size, basically. So that's a good way to do this. Just add your step size every step of the way. So the next midpoint will be 1/4 or 2/8 further along. So that'll be 5/8. And then you can't go any further. Well, yes, you can. There's one more, 7/8. There we go. All right, so those are our midpoints. We have 4 of them, which makes sense because you have 4 subintervals. Again, if that confused you, all I did in each interval here, so this interval right here, between those 2 edges, I computed their average, the halfway point. That ends up being 1/8. Let me erase this and just scoot that 1/8 over so that it fits nicely here, 1/8. And then in the next group, again, I computed their average. Their average was 3/8, but in reality, I rarely do that. I actually just add the step size. The step size was 1/4 or 2/8. 2/8 plus 1/8 is 3/8. And then the next interval would be 5/8 and yada, yada, yada. So those are our midpoints. So the midpoint method uses the same Riemann sum that we've been using all along, except the x sub I is traded out for the average, right? So we start at 1, we go to 4, we're evaluating our function at the average, x sub I minus 1 plus x sub I over 2, and then times delta x. But again, our delta x is still 1/4, and we have our averages written in green, so this is going to be f at the first average, 1/8, plus f at the second average, 3/8, and so on and so forth down the line, 5/8 and 7/8. And then you multiply that by the delta x, 1/4. Now this one, I'm actually going to quickly grab a calculator to compute, and we get exactly 1.5. Now, let me just tell you, because I said this at the very beginning, that you could just have used arithmetic in this problem. And this is a lesson learned. This is something that you should be very aware of, and I reward my students with this. When I give you a problem and I say, find the area underneath this curve, if there's a better way to do it than calculus, please do. Algebra, well, I should say arithmetic before algebra, algebra before trig, trig before pre-calculus, and pre-calculus before calculus. Calculus should be your last step. And we, just looking at that triangle, can easily say the area is just 1/2 base times height. The base is 1, the height is 3, that's going to be 1.5. So I could have easily just started this problem and said, well, let's not bother. I could just do this without calculus. I highly recommend you think as geometrically as possible in calculus so that you can not do calculus when you don't need to. The very final example in this video is going to be one where we're going to use a calculator. I want to show you how to do these computations without, well, for large computations like L sub 40. Nobody wants to add up 40 values. And so I want to just make sure that you know how to use technology to help here. This is not to say that you should always use technology. That is not true. Technology is only there when you can't do it by hand or when it's pretty much impossible to try to do by hand or very tedious. But for the most part, most instructors or professors will only hand you stuff that you can do by hand on exams. When it comes to homework, every once in a while you have something that requires a calculator. anything that requires me to do something beyond 8 slices, I tend to just quickly grab a calculator for. So let's go ahead and showcase how that's done. And by the way, I'm not only going to do L40, I think we should do M42 because we just, not M42, but M40 as well, because we've just learned the midpoint rule. So let's go ahead and use both. Well, L sub 40. Well, let's see what that looks like before we grab a calculator. So calculator should be the last thing you grab here. L sub 40 should be the summation I equals 1 to 40 of f of x sub I minus 1, right? Because you're using left edge of your interval that goes from x sub I minus 1 to x sub I. You're using that left edge. And we also know that delta x is going to be b minus a over n. So in this case, our interval goes from 1 to 3, so it's 3 minus 1 over 40, because it's 40 slices. So that's going to be 2 over 40, or in other words, 1/20th. Also, x sub I is going to be a plus I delta x. But in this case, we're not computing with x sub I, we're computing with x sub I minus 1. So let's go ahead and take a look at x sub I minus 1. I'm going to erase this, and I'm going to say, well, instead of x sub I, it's x sub I minus 1. It's still a plus, instead of I, it's I minus 1 times delta x. Okay. A in this case was 1, so I'll just plug that in, plus I minus 1 times delta x, which we've just computed to be 1/20th. I'm going to insert all of that information into the summation formula. This is going to be the sum of I equaling 1 to 40 of f evaluated at, let's see, 1 plus the quantity I minus 1 over 20. There we go. And we're multiplying that by delta x, which is 1/20th. Obviously, I could just move the 1/20th out. So I'm going to do that. 1/20th summation. I equals 1 to 40 of f at 1 plus I minus 1 over 20. All right. So how do you use a calculator on this? Well, that's the nice thing about Desmos. If you're using a graphing calculator, I can't really help you too much there, mainly because I don't use graphing calculators anymore. I haven't since, I think, around the late 90s. I mean, I use them if I have to, but generally speaking, they're kind of worthless now. So the way you're going to do this, I would recommend, is just use Desmos, or you could technically use Excel as well. The way we're going to actually find the summation using Desmos is not through the scientific calculator. The reason why is because their scientific calculator in Desmos cannot do sums. However, their graphing calculator can. So the way I do it is I'll type in the function. The function that we had was the natural log of x plus the cosh. Now, if they don't have the cosh, oh, they do have the cosh. That's good. So if they didn't have the cosh, I'd write it in exponential form, but that's fine. They have the cosh. And what we're going to do is just type in SUM for sum. And notice their index is with an n. That's fine. I'm going to sum from n equals 1 to n equals 40. And we'll go ahead and put f of, and remember it was 1 plus a fraction where the numerator was I minus 1. We're going to change it to n minus 1 because, well, our index is n here, not I, over 20. And notice it gives me a numerical value. I should note here that we need to actually multiply this by 1/20th because that was the delta x, or yeah, that is the delta x. So we get down to we'll round to the 9.9. So the area is roughly 9.9. And there we go. We have roughly 9.9 right there. One thing I want to mention is when we move on from here, you'll see that this number will not say 9.9 because I realized I didn't multiply by 1/20th when I finished that computation, so I had to go back and fix it. But I didn't want to, I was too lazy to fix the rest of the video. So you're going to see this number change. Just ignore the change. This answer is supposed to be 9.9. Now let's suppose instead that we wanted to compute m sub 40, the midpoint method using 40 slices. Again, I would just say, okay, the Riemann sum for that is going to be I equals 1 to 40. We're adding up all those areas. We have some function values times some widths, heights times widths. The heights are x sub I minus 1 plus x sub I over 2. Sorry, the heights are evaluated at x sub I minus 1 plus x sub I over 2. They're the average x values. So how are you going to do this like we did in Desmos? Well, it's a little extra work, but not too much. If you think about x sub I minus 1 plus x sub I over 2, well, we know that x sub I minus 1, if you go to our formula right here, we had written that already. X sub I minus 1 is this picture right here. It's 1 plus I minus 1 quantity, and then we had times delta x, which is 1/20th. So I'm going to write that in. In fact, maybe I should write it like this. Normally, x sub I minus 1 would be a plus I minus 1 times delta x. That's probably the better way for me to talk about this. And to that, we're going to add x sub I, which is a plus I delta x. That's x sub I. And this piece is x sub I minus 1. And we're going to divide that whole statement by 2. Well, this becomes, let's see, we have 2 of those a's upstairs. If I distribute this delta x to each of these terms, I'll have an I delta x minus delta x, and I have another I delta x right here. So I have a positive 2 of those I delta x's. And remember, I still have a minus delta x because of that distribution right there. And this is all over 2. I suppose I could rewrite this as breaking this into 2 fractions to where it's just a plus I delta x minus 1/2 delta x. Okay, so this is just me breaking this fraction like this into 2 subfractions, kind of like this, and then cleaning things up. Now I'm going to insert what delta x is and what a is from our work up above. Delta x is 1/20th, a is 3, or 1, sorry, a is 1. So let's go ahead and insert that in. We have 1 plus I over 20, because remember, delta x was 1/20th, yeah. Minus 1/2 of delta x, or in other words, 1/40th. And I could write this as 39/40ths plus I over 20. And now I could just go back over here, because that's the 39 over 40 plus I over 20 is what this argument of f is going to be. So this is going to equal, I'll move the delta x out. So it's 1/20th the summation I equals 1 to 40 of f evaluated at 39 over 40. And I think it was just minus, nope, plus I over 20. Let's go ahead and go to Desmos and finish this out and get our approximation using the midpoint rule. So going back here, we got our old work, right? Now all we really need to do is adjust the argument. And the argument's not going to be too terrible to adjust. Remember, we have to write it in terms of n, but it was 39 over 40. And then what, plus I over 20? So there we go. Oops, not I, sorry, n. There we go. And we get an approximate area of 10.13. And by the way, that area will, I'll say 10.14. That area is probably much more exact, definitely much more exact, at least twice as exact as the previous one, maybe even 4 times as exact. So anyhow, that is how you could use technology to help you evaluate a Riemann sum if you have a lot of slices. Don't rely on it for problems that have fewer than, let's say, 10 slices, because you want to get that practice, because when it comes to an exam, you're going to need to be able to do it by hand. All right, I'll see you in the next video when we wrap up this topic.
It's the system of equations. We must deal with them all at once. Always looking for solutions. complex, more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much, that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.